What's up, everybody? It's Dan from SageMathTutoring.com, and here's a video for a calculus student of mine who is facing these problems. And I actually found the first one in particular to be something that I had to really put some thought into, and pretty sure I got it. So I just want to make a video about how to do this one, and hopefully that's going to be helpful to my student as well. So anyway, looking at this first one, we're going to do all these, but let's just look at the first one. So typically when you're doing these limits, it's sometimes a good idea to just plug in the 5 just in general. Clearly we get an undefined situation here if you plugged in 5 for x. If you plugged in 5 for x here, that would also be undefined because it would be 5 minus 4 here, which would be ln1, and ln1 is equal to 0. Okay, so for my student who is at school right now, just know that, e to the 0 power equals 1, and that's why. Okay, so once again, ln of 0 equals 1, so you could always verify that sort of off to the side. But nonetheless, this would be undefined, this would be undefined. But in reality, they're not actually asking what the limit is as x approaches 5. They're asking what is the limit as x approaches 5 from the right-hand side. So as we have sort of, we get closer and closer to 5 from the right-hand side, which, we're going to get these little incremental values above 5, like, 5.1, 5.01, 5.001, 5.00001, right? Getting infinitely closer to 5 from the right-hand side. Now, if you think about that, as you get closer to 5, this is going to get closer to 0, which makes this a smaller fraction under here, okay? As you get closer to 5 here from the right, if it's 5.1, then 5.1 minus 5 would be just 0.1. If it's 5.01, well, 5.01 minus 5 would be 0.01. So as you can see, the difference is getting smaller and smaller, and it becomes this little decimal, also known as a fraction down here, that gets very small. So since this number is getting really small, that results in a scenario where this numerator outside is way bigger than the denominator. And whenever that's the case, whenever the numerator is much larger, relatively speaking, than the denominator, then we call that infinity. The whole thing becomes infinity. So you're going to want to think of these top-heavy fractions where this is really small, but this maybe just stays the same. But relatively speaking, it's getting infinitely larger than whatever's going on down here. So that's going to be infinity, okay? So far we have an indeterminate form where it's infinity minus something else. Well, let's take a look at this. When we plug in, values of 5 that are just above 5 here, well, this becomes this really tiny number, which means that it's going to be e raised to some fraction to get that tiny number here, okay? So as this number gets smaller, well, the whole thing gets smaller, we could say, okay? As the number inside the parentheses gets smaller, then the whole ln of x minus 4 gets smaller. And for the exact same reason as this one, where the 1 stays the same, but this gets just smaller, 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 well, that's going to be another infinity. All right. So for my student who is in school right now, if you have to kind of review that information, play it back a couple times, make sure that that makes sense to you, because the first thing you need to do is verify sort of the fact that you are indeed dealing with an indeterminate form, and this is one of the indeterminate forms that you're going to want to look out for, is this infinity minus infinity thing. Well, what do we know about L'Hopital's rule? Well, we know that once you have an indeterminate form, at that point, you can take whatever fraction you're dealing with and then take the derivative of the numerator and the derivative of the denominator, and then once again apply the same process to the result, and hopefully you're actually going to get a number as opposed to a weird indeterminate form. But in order to apply L'Hopital's rule, you have to have a single fraction. Now, we do not have a single fraction here, so we're going to have to turn that into a single fraction. How do you do that? Well, the way you could do that is we'll just kind of write the entire situation off to the side down here. We would have 1 over x minus 5 all over 1 times 1 over ln x minus 4. Well, we could just get a common denominator going where we have this as ln x minus 4, ln x minus 4. Over here it's x minus 5 times x minus 5. And then at that point, we would have the common denominators that we need. And in fact, that common denominator would be this ln x minus 4 times x minus 5 all over ln x minus 4 minus the entire quantity of, x minus 5. Okay, now let's just simplify that numerator. We're looking at ln x minus 4 minus x plus 5. And then over here, I'm going to say let's leave it in that sort of factored form. Okay, so what we've done at this point is we've turned this into a single fraction. So now we can actually apply L'Hopital's rule, where we are now going to take the derivative of the top and the derivative of the bottom. Now, let's focus on the derivative of the top. Derivative of the top, I'm going to use an arrow, not an equal sign, because we're finding the derivative. We're not, what I'm about to write does not equal the red thing, but what I'm about to write is the derivative of the red thing. So up top, we're going to have 1 over x minus 4. That's the derivative of ln x minus 4. And that's just going to be minus 1, because the derivative of this is just 1. The derivative of that is 0, so I don't even have to write that. Okay, so we have that all over. This would be a product rule situation. So we have all this. We have, let's just keep this first one as is. That should be x minus 4. And this would be 1. The derivative of this guy is 1. And then we're going to have 1 over x minus 4. That's the derivative of ln x minus 4 times the original x minus 5. Now, I believe we could then simplify this further. We have 1 over x minus 4 minus 1 all over, looks like it's ln x minus 4 plus, let's see, x minus 5 over x minus 4. So what happens when we take the limit as x approaches 5 from the right here? Well, if we were to approach 5 from the right here, this would get closer and closer and closer to 1, actually, if you think about it, right? Because even if you imagine you just put 5 in there, well, that would be 5 minus 4, which is just 1. So that would be 1 minus 1. So that would be a 0 up top. And then over here, as x approaches 5 to the right, this is going to get closer and closer and closer to 1, which makes, the whole thing getting closer and closer and closer to 0. So that would be all over 0 plus, let's see what's going on over here. We would have this would get closer and closer and closer to 1, and this would get closer and closer and closer to 0. So if this is 1, and this is 0, that would be 0 over 1. So that would just be 0. So we have another indeterminate form, only this time the indeterminate form is 0 over 0. So what does that mean? Well, we have an indeterminate form, so that means we could take the derivative of the top and bottom again, okay, as though you weren't having enough fun already. Now you have to take the derivative again. So how are we going to do that? Well, first of all, let's realize that this one is really x minus 4 to the negative 1, and it's going to be that minus 1. And let's do the derivative of that one first. So once again, I'll just use an arrow for the derivative. So when we do the derivative of this green thing, well, that's going to be negative 1 in front of x minus 4 times, and that's negative 2 also, times the derivative of x minus 4, which is just 1. So I actually don't have to write that. But that would be a chain rule situation. So you apply the power rule first, bring the -1 out, drop this down by 1, it becomes -2, and then multiply it by the derivative of what's inside the parentheses. But the derivative of what's inside the parentheses is actually 1, so I don't have to write that. The derivative of -1 is just 0, so I don't have to write that either. So I'm going to go ahead and draw that. The derivative of this one is 1 over x minus 4. And the derivative of this would be a quotient rule. So what we're looking at there is we would have this kind of fraction. You would have this x minus 4 squared. You'd bring the x minus 4 up here. You would multiply that by the derivative of this one, and that would just be 1, so I actually don't have to write that. And it's going to be minus a derivative of x minus 4, which is just 1, times the original numerator, which is x minus 5. So I'm just going to keep that in parentheses as well. We're going to do a little bit of simplification after, and by after I mean now. So we have the numerator is really just -1 over x minus 4 squared. Down below we have 1 over x minus 4 plus definitely x minus 4 squared down here, right? And then we have this x minus 4 minus x minus 5. So that would be, looks like the x's would cancel, and we would have a negative, or we'd have a -4 plus 5, which is just a 1. Okay, so that's interesting. So that whole thing would become a 1 right there. So then, what the hell is going on with this? What is this? Well, we could, plug in the 5 now. I think it should work out actually now. Yeah. So if you were to approach 5, from the right, well, we get closer and closer to 5. You can imagine if you put 5 in here, it would be 5 minus 4, which is just 1. So actually, that would work. We could say it's going to be -1 over 1, and 1 squared, right? If you put 5 in there, it's going to be 1. If you get, put numbers that are infinitely closer to 5, well, that would result in a number that's infinitely closer to 1 being squared. So we might as well just call that 1 squared, which is just 1. Okay, so I'll just write 1 over 1 just to sort of highlight the fact that that's what we did. This would be the same thing, and this would be the same thing. So it would be 1 over 1 plus 1 over 1. And I think you could see that that would clearly be -1 over 2. So that's -1/2. So that should be the answer to that one. If you were to graph that, what you should see is that as you approach x equals 5 from the right on the graph, it appears as though y is approaching -1/2 or -0.5, okay? So that is that one. Now, let's say you didn't like this fraction. Just for the record, one thing you could have done is you could multiply the top and bottom by the LCD, the least common denominator, and that would have knocked out these denominators and made it sort of a less clunky looking thing. But the bottom line is this is a result of taking the derivative of the top and bottom, so it's worth checking perhaps if we could just apply the limit from that point forward. All right, and we did, and we discovered that it was -1/2. So that's that one. Let's see, L'Hopital's rule, evaluate the following limit. Well, it's already a single fraction. If you were to put infinity here, it would be infinity inside of here, because it's 10 times infinity plus 3, so that's basically infinity. And then e to the infinity would give you infinity. So far we're looking at an indeterminate form where we have infinity on the top. And for the exact same reasons, this would be infinity as well. Now, infinity plus 5 is really just infinity. So we could, certainly acknowledge that that's the indeterminate form, which means that we can now go ahead and just take the derivative of the top and bottom, and that would be 1 over 10x plus 3 on top times, it's a chain rule situation, times the derivative of 10x plus 3, which is just 10. I'm going to simplify that, make it look a little better later. Down here, it's going to be 1 over 6x plus 9, and we will be multiplying that times the derivative of 6x plus 9, also known as 6. When we take the derivative of 5, that just becomes 0, so I'm not going to worry about that. Now this becomes 10 over 10x plus 3, that's the top, all over 6 over 6x plus 9. In reality, what we have here is a fraction divided by another fraction, and that would be a keep, change, flip scenario where you keep the first fraction, change the operation to multiplication, and then flip the second fraction. So this becomes 10 over 10x plus 3, and that's times 6x plus 9 all over 6. At that point, I'm happy to call that a 5. I'm happy to call that a 3. I don't think there's anything else we can do. So at that point, we would have really 30x plus 45 all over 30x plus 9. And that would still result in infinity over infinity if you were to plug infinity in there. So we could do the derivative again. And the derivative again of the top and bottom would be 1 over 1, because the derivative of 30x is just 30, and this would be 0. The derivative of this would be 30, and that would be 0, so it would be 30 over 30, which is 1 over 1. Okay, I kind of just did all that in my head, so hopefully that makes sense. I'll say it again. Once again, the derivative of this will be 30, the derivative of this will be 30, and 30 over 30 is just 1 over 1. So the limit as x approaches infinity of this one is 1. So if we want to find the horizontal asymptotes of this and that, well, we're just going to focus on this one for now. That's essentially saying, what's the limit of this as x approaches infinity, all right? That would tell you where the horizontal asymptote is, okay? So, well, let's see. We have a situation here where, first of all, we just write it, right? X approaches infinity. Then we have x over 7 times tan of 7 over x. Well, when we plug in infinity right away, we're going to have infinity over 7 times this number. Now, as this approaches infinity, okay, that would turn this into a 0, because anytime you have a bottom-heavy fraction like that, where there's infinity on the bottom, then that's 0. The whole thing is 0, okay? So that would be tan of 0. Now, tan of 0 is 0, okay? It would be 0. So this would result in an indeterminate form where this guy is infinity, but this one is 0. And that's one of the indeterminate forms that you're going to have to kind of look out for. So, well, before we do L'Hopital's rule, we'd have to turn this into a single fraction. Now, it's not really a fraction that we can work with yet. So let's see, we would have x times tan 7 over x up top. And we can say that that's over 7, but the problem is we don't have a function down here. So typically you're going to want a function over another function before applying L'Hopital's rule. So 7, the reason I'm not calling it a function is because it doesn't have x. You want a function that features x down here and a function that features x down here. Now there is something that we could do where we could realize that we do have this x right there, and there's a move you can make where you can put tan 7 over x all over 7 times 1 over x. Because if you think about it, this divided by 1 over x is the same as this times x, which is what we have here. So that's something to try. That's something to consider. That's something to try. I'm just going to simplify that a little bit. We have tan 7 over x. I'll keep that in parentheses. Over 7 over x. So that's what we're working with. And now when I take the derivative of the top and bottom, well, the derivative of tan is secant squared of this. But the derivative of, if we were to take the derivative of 7 over x, that would be really 7 times x to the negative 1. And the derivative of that is negative 7 times x to the negative 2, which is really equal to negative 7 over x squared. So that would get tacked on at the end. We'd have negative 7 over x squared as well, being multiplied to the secant squared, 7 over x. And over here, we would have that very same derivative actually down below. So that would become negative 7 over x squared. Now it's looking like these will cancel. That's probably a good sign. We're going to find out. So what we have left over is just that. Now, originally, let's see, we're plugging in infinity. So if we were to plug in infinity down here, if we were to do the limit this time, I should probably write that. Then this would be secant squared of 0. And secant squared of 0, let's just think about that. Secant squared of 0. It's really secant of 0 squared. And secant is the reciprocal to cosine, and cosine of 0 is 1, and the reciprocal of 1 is 1, so this should just be 1 squared, which equals 1. All right, so that's how you'd want to do this one. Now, I think that's a good way to just notice that the x is here, so that could be represented as 1 over x down below. Now, there's a part of me that wonders if we had turned tan into sine x over cosine x, sine of 7 over x over cosine of 7 over x. There's a part of me that's kind of wondering whether or not that would have worked as well, and there's a chance it may have. All right, so anyway, that's that one. Okay, so with this one, when you attempt to take the limit as x approaches infinity, we would have 3x plus e to the 2x, 2x plus e to the 3x. Now, this would become infinity plus infinity, which makes it infinity. This would become infinity plus another infinity, which makes it infinity. So you'd have infinity over infinity, which is a problem. Now, I can foresee that there's going to be an issue because every time we take the derivative of the top and bottom, we're just going to end up with an e again, an e to the something x power again every single time. And it's going to result in infinity, I think. So let's see. This would become 3 plus e to the 2x times 2, right? So that's a problem. Because if you think about it, this would be 3, actually. 3. There's my correction. So basically, this would become infinity here. So it would once again become infinity over another infinity. So that's a problem. So there's a trick you can do where you can multiply the top and bottom, or we could say even divide the top and bottom by the um, e to the 3x. Basically dividing the top and bottom, we could say multiplying the top and bottom by 1 over e to the 3x, because that might simplify things down in a way that works for us. Because at the very least, it's going to turn this thing into a 1. All right. So in other words, multiply the top and bottom by some kind of a fraction that would force one of these guys to become 1, and therefore I'm choosing this larger exponent of 3x. So I think you would agree that we could distribute here, we could distribute there, and then as a result of that, what we're really doing is taking the limit as x approaches infinity of, let's see, 3x over e to the 3x plus, okay, now let's think about it. E to the 2x over e to the 3x, that's going to be 1 over e to the x. So for my students watching, maybe just confirm that on your own. This times that is going to result in that. We would have 2x all over e to the 3x here, and then we would have plus 1. Now, what I'm seeing is there's a possibility we actually don't need to use L'Hopital's here, because look at what happens when we plug in infinity now. So we would have infinity here, but we'd have this infinity that's sort of increasing much faster than this infinity. So for my student in school, just know that, yeah, you may remember those notes where if you have like an exponential function, that sort of trumps a linear function or a polynomial function in terms of how quickly it's increasing. So this bottom is increasing like really, really fast compared to the top, which makes this 0. So anytime you have a bottom heavy fraction in that way, that's just going to be a 0. So if you were to plug in infinity, that would become 0. And really for the same reason, this thing would be 0. So we already know that the numerator is going to be 0. But then this would be 0. Okay, so this is turning out to be easier than I thought. This is going to be 0, and then we're going to have 0 plus 1. And that's going to just equal 1 down below. So we have 0 over 1. And then we are good to go. That is 0. Okay. All right, so I hope this was helpful for everyone watching. I'm kind of just working through this stuff on the fly. And thanks for sort of being patient with me thinking through it sort of in real time. Now, for those of you watching, if you've noticed any careless mistakes, just let me know in the comments below. Pretty sure the final answers are correct, though. And I will talk to you guys later. Take it easy.